In this video, you will see how the equations of a plane, the vector and scalar equations, in a three-dimensional coordinate system can be obtained from a point on the plane and a vector perpendicular to the plane. As always on this channel, you can expect a clear and concise explanation of each topic. Please don't forget to click on the like button, subscribe to our channel and activate the notification bell. Your support is crucial for our channel's growth and enables us to continue creating quality content. Thank you in advance for your support. Let's start from the straight lines. We know that a line is determined by 2 points, and you saw in the previous 2 videos how an equation of a straight line in space can be obtained from a point on the line and a vector parallel to it. Although a line in space is determined by a point and a direction, a plane in space is more difficult to describe because a single vector in a plane is not enough to convey the direction of the plane, since the plane is free to rotate about the vector. In fact, there are infinitely many planes containing the given vector. Now imagine a pair of orthogonal vectors that share an initial point P. Visualize grabbing one of the vectors and twisting it. As you twist, the other vector spins around and sweeps out a plane. So, as I said before, a single vector in a plane is not enough to convey the direction of the plane, but a vector orthogonal to the plane does completely specify its direction. This orthogonal vector is called the normal vector. You may be wondering, but there are infinitely planes perpendicular to vector n. Yes, it is true. But if I take a point P prime in the plane along with the vector n, then that plane will be unique. Thus, a plane in space is determined by a point P in the plane and a vector that is orthogonal to the plane. Now we describe that concept mathematically, and you will see how the equation of a plane in space can be obtained from a point in the plane and a vector normal to the plane. Consider a plane that passes through a point P. We can determine this plane completely by specifying a non-zero vector n that is orthogonal to the plane. Such a vector is called a normal vector. Basing vector n at P as in figure, we see that a point Q lies on the plane precisely when the vector PQ is orthogonal to vector n. Remember, the dot product of orthogonal vectors is 0. This fact generates the vector equation of a plane. If the normal vector has components a, b, and c, then we can write this equation in component form. Then the vector equation of the plane becomes. Performing the dot product, we arrive at the following equations of the plane in the variables x, y, and z. This equation is called the scalar equation of the plane, or standard form of the equation of a plane. By regrouping terms in the standard form of the equation of a plane, and when we set the left-hand side equals d, we obtain the general form of the equation of a plane. We now summarize the results as follows. Equations of a plane. The plane through point P with normal vector n is the set of all points Q satisfying the equations. Vector equation of a plane. The standard form of the equation of a plane. The general form of the equation of a plane. We will now see how to write the equations of a plane with some simple examples. Find an equation of the plane determined by the points P, Q, and R. In both standard and general forms, find the intercept and sketch a graph of the plane. We know that given any 3 points that do not all lie on the same line, there is a unique plane that passes through these points. To write an equation for a plane, we need a point in the plane and a vector that is normal to the plane. We start by identifying two vectors in the plane. The vectors PQ and PR lie in the plane, so their cross product is normal to point P and can be taken as the normal vector. So we find the normal vector by taking the cross product between these vectors. We can use this normal vector together with the coordinates of any one of the three given points to write the equation of the plane. Using point P leads to the equation of the plane in standard form. By regrouping terms, the general form is given as follows. Before we solve item B, I must explain what trace means in the context of the study of planes in space. If a plane in space intersects one of the coordinate planes, then the line of intersection is called the trace of the given plane in the coordinate plane. We obtain the trace in the xy plane by setting z equals 0 in the equation of the plane. The trace in the xz plane is obtained by setting y equals 0. And the trace in the yz plane is obtained by setting x equals 0. Now we can go back and sort out item B. To sketch a plane in space, it's helpful to find its points of intersection with the coordinate axis. We can find the x-intercept by letting y equals 0 and z equals 0 in the equation of the plane and solve for x. Similarly, we find the y and z intercepts. We obtain the trace in the xy plane by setting z equals 0 in the equation of the plane. Similarly, the trace in the yz plane is obtained by setting x equals 0, and the trace in the xz plane is obtained by setting y equals 0. The intercepts enable us to sketch the portion of the plane by sharing the triangular region as shown in the figure. In the previous example, you learned how to write the equation of a plane when the 3 points are given in the plane. In this example, you will learn how to write the equation of a plane when given the normal vector to the plane and a point in the plane. We are given the point P in the normal vector. So, if we put these values into the standard form of the equation of a plane, we obtain after multiplying out the terms and simplifying, we obtain the general form of the equation of the plane. Find an equation of the plane that passes through point P and contains the line given by. In this example, you will learn how to write the equation of a plane when are given a point and a line in the plane. we are given the point P and the symmetric equations of the line. So we start by rewriting the symmetric equations to obtain the parametric equations of this line. Then the symmetric equations of the line become the parametric equations of the line. From the parametric equations, we can see that the line passes through the point that I will call Q with coordinates x equals 2, y equals 3, and z equals 1, parallel to the vector v given by. Now we will use the point Q and the given point P to identify a second vector parallel to the plane. So we write the vector PQ. To find the normal vector n, we use the cross product between vectors PQ and V. Now we use the given point P and the normal vector to obtain an equation of the plane. In this last example, you will see how to find the point of intersection between a line and a plane. In fact, this is a very simple example to be solved. The line has parametric equations. We simply substitute x, y, and z in the equation of the plane and solve for t. Simplification yields t equals minus 3, and by substituting this value in parametric equations, we obtain the intersection point. I'm going to finish the video here so it doesn't get too long. In the next video, I will cover complementary topics about plane equations, such as intersecting planes and distance problems involving planes. See you in the next video.